Hello everyone, this is Mrs. Lindsay. Today we're going to talk about natural exponential functions. So in other words, let's start with E. What is E? E is a rational, an irrational number that is approximately 2.718. E is for Euler. And what do we mean by an irrational number? Well, probably the most famous of them all is pi. Okay, the unformal definition is where the decimal does not repeat and it goes on forever. Okay, so why would we choose to work with such an odd value? And it might seem like a strange choice, but you can see when we get some calculus involved, with some exponential and logarithmic functions, you'll see that coming up, that it's can be quite a convenient choice and where some other bases are not. And this is actually the formal definition at the bottom here. E equals the limit as x approaches 0 of the quantity x plus 1 plus x raised to the 1 over x. Okay. And since E is actually 2.718 ... etc., if we actually graphed this function, hopefully you realize again this base is greater than 1, so that's going to be an exponential growth model. So it'll look something like this. Okay. All right. So we have logistic growth functions. Okay, and this is an example of that. So let's try one here. A bacterial culture is growing according to this model, where t is greater than or equal to 0, and y is the weight of the culture in grams, and t is time in hours. We want to find the weight of the culture after 0, 1, and 10 hours. So what we're going to do with this is literally plug in for time, right? Because this is time. We're going to plug that into, I'll make a chart. So my x's are really my t's here. And my function f of t, I'm going to plug in 0, 1, and 10. So if you don't have your calculator, go ahead and pause and grab that. So we are definitely going to graph this and then see what it looks like in our calculator, as well as find these values. Okay, so let me move this over. Alright, so now we can actually go to y equals. There's a couple different ways to do this. The first way is to graph it, but let me show you the other way first. So if I want to literally just plug 0 in to my function, I'd have 1.5 divided by, and please put parentheses around the entire denominator. So it would be 1 plus 0.2 e. So I'm going to push second. And it's right next to it's above the ln key by the 4 key. So e raised to the negative 0.5 times 0. And then I will close my parentheses. So we get that to be 1.25. Go ahead and grab my... And I can do the same approach to plugging in 1 and plugging in 10 as well. But let me show you how you can actually graph this as well. I want to show you the graph, and then we can find our other values there. So we'll have 1.5 divided by, and again, parentheses around the entire denominator. Second e raised to the negative 0.5x. And I'm going to close my parentheses. And I want to start in the standard window. So I'm going to go ahead and push the zoom 6 just to make sure I start in that, again, standard window there. Okay. Now let's go ahead and fill in the rest of this table here. So if I go to my table and my calculator, you can see we already have 0 in there is 1.25. 1 has a value of, let me put that back up there, 1.3377, and then we also have 10, which is 1.498. So let me go ahead and fill those in to our table. So these are our weights and grams for when we have 0, 1, and 10 hours. So these are our weights in grams. So let's think about this next question. What is the limit of the model as t approaches infinity? So what is the limit as it approaches infinity of our model? Well, hopefully you're thinking about as it approaches infinity, horizontal asymptote. So let's take a look at our graph here. So with our graph, it looks like we can even just push trace just to try to get a ballpark idea. What is our y value approaching here? You can see 1.38, 1.39, 1.5. As x is getting increasingly large and large and large. 1.48, you can see it's slowing down. 1.49, 49, 49. It's sticking with 49, 49. So our actual horizontal asymptote, let me go back to the graph, I forgot a decimal point, is 1.5. Okay. So again, this is with these logistic growth functions, these really have what we call a carrying capacity. So they have, it reaches a size where an environment can't go over a certain value. And this is an example of one of those. Another model that you're probably a little bit more familiar with is in terms of compound interest. So go ahead and pause this, write these down, and then we'll talk about the meaning of them and how we'll use them. And this does say compounded continuously down here in blue. Okay, so go ahead and pause and then write those down. Okay, so with compound interest, we have two different formulas. The one which we typically would call PERT, P-E raised to the R times T. This is using E, right? This is our natural exponential function. And then we have P times the quantity 1 plus R divided by N raised to the NT. This is for when it's compounded yearly or monthly or daily, anything besides continuously. If it ever says it's continuously, you're using PERT, okay? And all these values apply. A, P, R, N, T are the same for both functions. So let's try an example with this. All right, so nominal or stated rate and the effective rate. We'll get to this in just a moment. Let's go ahead and first try our problem, and then we'll come back to the effective rate. If you deposit $2,600 in an account with the stated rate of 4% interest, what is your balance after 5 years of monthly compounded interest? So key word here, monthly compounded interest. So that tells us which formula that we are going to use, and that formula is going to be P times the quantity 1 plus R over N raised to the NT, because it does not say continuously. So let's go ahead and write that down. So I'll use A equals P times quantity 1 plus R over N raised to the NT. So what do we know? We know $2,600. That is what we call the principal amount. It's our starting amount. We also know that we have a rate of 4%. So as a decimal, that would be 0.04. What is your balance after 5 years? So that is going to be T. And it's compounded monthly, so that's our N values, and there's 12 months in a year. So we'll plug in 12 for N. That will give us our accumulated amount. So let's go ahead and grab out our calculator, and we'll plug this in. So now we have 2,600 times the quantity 1 plus 0.04 divided by 12 raised to the, and please make sure you take 12 times 5, whether you multiply it ahead of time and get 60, or just make sure the 12 times 5, the entire thing is the exponent. And then we'll push enter. And whenever we're dealing with money, you're always going to round to the nearest cent. So we have $3,174.59. So that'll be approximately $3,174.59. Okay, so let's now answer this second question, which is on your sheet there. What is the effective rate for this account? So let's go back up here and read what is effective rate. To determine your effective rate, calculate the interest on $1 for 1 year with whatever stated rate and compounded period you have, and then subtract 100% or 1. So again, let's read this again. Calculate the interest on $1. So in other words, your starting amount, P, principal, would be 1 for 1 year. So again, your time would be 1. So let's take again our amounts here. So we have $1 is going to be P. 1 plus, and it says use the stated rate, so the rate of 4% will not change. And it's also going to be using the stated compounding period, so the monthly compounded interest will still be 12. But now I'm going to turn my time to 1. So principal becomes 1, time becomes 1. So let's go ahead and plug that in. So I have 2,600 times, oops, I apologize, that would be 1 times 1 plus 0.04 divided by 12 raised to the 12. So that gets me a value approximately of 1.0407, I believe it was. Let me double check that. Okay. And then let's see what else it says up here. After we calculate the effective rate, we then must subtract 100% or 1. So if we subtract 1, we would get 0.0407, which gives us an effective rate. So again, we have to write this as a percentage, 4.07%. Yeah, convert that decimal to percent. That would be our effective rate for this account. Okay, and that concludes our lesson on natural exponential functions.